Hi, welcome to Videos on Control Systems. So in this video we shall do a recap of basics of control systems. Before I start, so since we are starting with the basics of control systems, so you should be by this time aware of open loop, closed loop transfer function, poles, zeros, root purpose gain and system gain. And you should also be knowing, okay, how do we reduce the transfer function using block diagram and signal flow graph. And we'll also be touching upon modeling of electrical and mechanical systems to find their transfer function. Okay, these initial now we shall start with representation of a system. We know that we can represent a system using a very simple block diagram, something like this. This is RFS, which happens with the reference input. CFS is the output, and GFS is the Laplace transform of the forward transfer function. HFS is the feedback transfer function, or Laplace of the feedback of the transfer function network. We have two possibilities of feedback. So feedback can be either negative feedback or positive feedback. Let me say this is negative with red and positive with maybe a blue one. So let us write the transfer function corresponding to open loop transfer function, which is nothing but you open the loop and try to multiply GFS into HFS. So this is GFS into HFS. This is the open loop transfer function. This is open loop transfer function. Maybe we can also define BFS is the feedback signal, EFS is the error signal, and if you say this is plus and all those stuff, and from this we can say BFS, the feedback signal is CFS multiplied by HFS, and EFS can be written as RFS, of course, minus or plus of BFS, depending on the type of feedback. And we will define open loop transfer function as GFS into HFS. And what is a closed loop transfer function? So when I mean closed loop transfer function, it is output CFS by RFS. So this happens to be GFS by 1. Okay, it will be 1 plus GFS into HFS if the feedback is negative. If the feedback is positive, it is minus. So it is GFS by 1 plus GFS into HFS if it is minus. If it is negative feedback, if it is positive feedback, it is GFS by 1 minus GFS into HFS. This is the closed loop transfer function. So if you are wondering, okay, what is this ratio? This ratio is nothing but BFS by RFS. So this is what is BFS by RFS. So this is a ratio what we are finding. And of course, we'll just keep this open here. So we'll not be closing the loop. That's what is open loop transfer function. Fine. So let us take some example in terms of representation of the transfer function. So let us assume that BFS is nothing but 10 divided by x plus 4 and HFS is 1, or maybe you can also take this as x plus 6, so on. So this is the transfer function. If this is a transfer function, then you can write it as something like this. This is 10 divided by x plus 4 x plus 6 divided by, so now you have this as, assuming that this is a negative feedback, this is RFS, this is CFS. If you want to write what is the open loop transfer function of this will be 10 divided by x plus 4 and x plus 6, and closed loop transfer function closed loop transfer function is given by cos 10 divided by s plus 4 into s plus 6 whole divided by 1 plus 10 by s plus 4 into s plus 6. Upon simplifying this, the closed loop transfer function reduces to the closed loop. This closed loop transfer function reduces to, this will be 10 divided by, if you can see, this is s plus 4, s plus 6 plus 10. Let me just rewrite this. So this will be s plus 4, s plus 6 plus 10. So this can be further written as 10 divided by s square plus 10s plus 24 plus 10. So this happens to be 10 divided by s square plus 10s plus 34. If you find the roots of it, then this will be, let me find the root of it. Sorry. So this is degree 2 quotient of 1, 10 and 34. So it is minus 5 plus or minus j. So these are the roots of it. So then, okay, let me write roots are minus 5 plus or minus j3. Then this will become s plus 5 plus j3 and s plus 5 minus j3. So now, so let us now talk about poles and zeros of the transfer function. So I have my open loop transfer function. Open loop transfer function is given by this. Open loop transfer function is given by this. 10 divided by s plus 4, s plus 6. Similarly for closed loop transfer function, I have the transfer function as, that's what is this. See, 10 divided by s plus 5 plus j3 and s plus 5 minus j3. So this is what is the transfer function of this particular block diagram. So now I can find out where are the poles. So we know that these are all poles. The denominator of your transfer function, the root will indicate the pole position, and since this is in pole zero form, so if you have the quotient of s as 1, then this is called as pole zero representation, and this is called as root locus gain. So this is what is called as root locus gain. So this, if it is in this form, is called as pole zero form of transfer function representation, which will always have s plus something, whereas this is always 1. So it is 1 into s plus x. So this x indicates the position of polar 0 depending on where is this term is. If it is in numerator, then that will become open loop 0. If it is in the denominator, it will become open loop pole. So this is in open loop pole. So where are open loop poles? The poles open loop poles are at -4 and -6. How do you represent that? The representation of open loop poles in S-plane would be, so this is my S-plane. So these are all negative values on the left hand side. On the right hand side is positive. So this is rho j omega, or okay, this is real values, that is imaginary values. And since it is real in number, you have this as -4, this as -6. This is open loop poles. And coming to closed loop poles, again this is in pole zero form representation, because you can see this is having a quotient of 1. Now if you want to represent this poles in the S-plane, now I can represent this in S-plane. Now the real part is -5 and the imaginary part is plus j3. This is j3, this is minus j3. You see the coordinates of these two will meet here, and now this is the pole position. So what is this pole position? This pole corresponds to this pole corresponds to this. So that's how you are representing the closed loop poles with this A as again the root locus gain. Locus gain. This is the pole position. Okay, now let us take the same open loop transformation, which is now equal to 10 by s plus 4 s plus 6 is there. So what I'll do, I make the plus term as 1 and plus term as 1. So how do I make this as 1? I have to take 4 outside, I have to take 6 outside. So then it is 10, of course, the same equation. When I take 4 outside, it will become s by 4 plus 1. When I take 6 outside, it will become s by 6 plus 1. So what is this now? This will become 10 by 24 and it is s by 6, sorry, s by 4 plus 1 and s by 6 plus 1. So now what is this? So you have, what is this now? So it is 10 by 24 is 0.416 divided by, so now it is, I'll write it as 1 plus s into 0.25, and because 1 over s, 1 over 4 is 0.25, 1 over 6 is, it is 1 plus s into 0.166. See now, this is exactly same as 10 by s plus 4 s plus 6. These two are exactly same. Now we set this as pole 0 form of transfer function. This is time constant form of transfer function. Both are same. So now what is this now? So this, we know that this is called as root locus gain, and this is called as system gain. Where is the pole position of this one? It's at -4 and -6. Where is the pole position of this? So it is nothing but 1 over tau. So this is actually in the form of 1 plus s. So what is tau now? It is nothing but 1 over 0.5, because it is minus. Where is this? It is -4. How about the second one? Second, okay, let me say it as tau 1. This is 1 plus s tau 2. Where is the pole? It's at in S-plane position, it is minus 1 over s tau. So what is this? It is 1 over minus 0.166 is nothing but -6. You see the open loop pole positions are -4, -6 both in pole 0 form representation and time constant form representation. The pole position doesn't change. The poles are at -6, -4, -6, -4. Only thing is that gain will be system gain here, gain will be root locus gain. So that's the only thing what you are supposed to keep in mind. So this is first one, second one, third. Okay, let us do one more such problem and try to understand more of it. So let us consider GFS as equal to 50 into s plus 5 divided by s into s plus 3 s plus 8. Let us assume that h of s is equal to 1. So I'm interested in knowing what is the open loop transfer function and the pole 0 positions. Pole 0 positions. So what is this now? It is 50 into x plus 5, because it is GFS into HFS, my open loop transfer function. Since HFS is 1, so whatever is your GFS, that becomes the open loop transfer function. It is S into S plus 3, S plus 8. So where are open loop poles? Poles are at origin, because this can be written as s plus 0. So this is your pole position. So one of the pole is at origin, other pole is at -3, one more pole is at -8. These are all open loop poles. What is the zero position? The zero position is at -5. What is the root locus gain? Root locus gain is 50. I can represent the same open loop trans function in time constant form also. So how do I do that? It is 50 into take 5 outside. Is it not 1 plus s by 5? So this s is as it is. I'll take out 3 outside. Is it not 1 plus s by 3? I'll take 8 outside. Is it not 1 plus s by 8? What are the positions? Now it is uh, 50 into 5 divided by 3 into 8. What is that? That will become 10.416. 1 plus, so what is 1 over point, okay, 1 over 5, it is 0.2, divide by s into 1 plus 0.333s and 1 plus 0.125 s. See now here in the what pole 0 representation, this the quotient of s is 1 and you have some number. Here the quotient of s is changed and here it is 1 plus 1 plus. So this is now system gain. This is, so now where are poles? Poles are still at origin, minus of 1 over 0.333, which is nothing but -3, and minus of 1 over 0.125, it is still -8. Since it is the same position, and where are zeros? 0 is at 1 over minus 0.2, which is nothing but -5. What is system gain? Only system gain changes. System gain is now 10.416. How did I got this 10.416? It is this into this divided by 3 into 8. So that's what is system. Let us find what is the closed loop gain of this. So closed loop gain of this, let us take this. Let's take this, because we know that closed loop transfer function is given by GFS by 1 plus GFS into HFS. Whenever HFS is 1, whenever it is unity feedback, you can simply write this open loop trans function, which is 50 divided by s plus 5 divided by s into s plus 3 s plus 8. So this is a part of your trans function. Then what you have to do, you have to add plus. What should be added here? So I'm trying to write the closed loop trans function. Closed loop trans function of a system when it's a unity feedback is nothing but open loop trans function. Write it as it is. You add one extra term in the denominator, which is nothing but HFS multiplied by the numerator. So HFS is 1. What is numerator? It is 15 into s plus 5. So now can I simplify this? It is 15 to s plus 5 divided by, so I will write it as s into s square plus 11s plus okay, this is 24 plus 50s plus 250. So then this becomes 50 by s plus 5. Then what is this? This is s cube plus 11 square plus 24 plus 50 is 74s plus 250. So the transfer function now, the closed loop transfer function is now 50 by s plus 5 divided by, find the roots of it. So what are the roots of it? So of third order it is 1, 11, 74 and 250. The roots are, okay, it is s plus 5.7 and s plus 2.64 imaginary, it is plus j 6.06 and s plus 2.64 minus j 6.06. These are the closed loop poles. So now, since it is in O0 form, see it is s plus something, s plus something. So this whole thing is the position of your pole. So where are poles now? Poles and zeros. Poles are at minus 5.7 minus 2.64 plus j 6.06 minus 2.64 minus j 6.06 and 0 is at minus 5. And how about the root locus gain? Root locus, of course, let me just, this gain remains as 50. Now we can just see where were the open loop poles. So open loop poles for the same thing were at, so this is at, one was at minus 8, one was at 0, one was at minus 3, this was at minus 1. See, these were the open loop pole positions. This is open loop 0 and these are closed loop poles. If I just write the transfer, if I write the explain representation, if I write using glue the open loop, this is open loop transfer function pole positions. So is it this, is it this, is it this, and is it this? Minus 5 for open loop, for the closed loop, this is still at same point. You can see, interestingly, the 0 position will never change. The 0 is at minus 5, the 0 is still at minus 5. It will never change. Only the poles will change depending on, of course, the value of k. How about this? This is there at minus, this is at minus 5.7 and this is at minus 2.64 and this is at plus j 6.06, this is at minus j 6.06. The red one are closed loop. Red is closed loop and blue are open loop. You can see 0 will have poles and zeros. Sorry, open loop and closed loop both are at same point because 0 will not move. Okay, this is about. Now we will also define something like dominant poles. Dominant poles are one which are closer to imaginary axis. So of course, closed loop dominant poles are usually vectored for a closed loop transfunction. In a closed loop transfunction, if you can see, I have this pole and these two poles. So these two poles. Now this is one pole, these two are the other poles. Now we will define, can you see, these are minus 5.7 here and minus 2.65 here. So the poles which are nearer to the imagined axis, it is this. So these two are called as dominant poles. I say these two are called as dominant poles. Dominant poles. Why it is called as dominant poles? Because they will going to dominate the frequency and time response of the system. The system response is dominated by or ruled or controlled by these two poles which are closer to imagined axis. So that's why the poles which are closer to imagined axis in a closed loop transfunction are called as dominant poles. Okay, fine. With this, we shall move on to. So we had first 1, 2, 3. Let me say this is fourth one. This is this is the 7. Let me say this is 8, 9, and 10. And now let us try to represent a transfer function or a system in the form of block diagram and try to find its transfer function. So now let me just consider a system having something like this. So you have a system with gain 5 as a system, okay, some gain, assume that this is 10 and these two are going to this summing point with plus and plus, and assume that I have this is having and divide by, so it assume that it has got poles at s plus 2 s plus 1, and assume that this is having a negative feedback, and let's assume that this is having an overall negative feedback from here to here. So this is RFS CFS. I'm asked to find what is CFS matrix of the system. So this is, if at all, if this is the requirement of finding the closed loop transfer function of this system, so it's very easy to reduce this and try to find the closed loop transfer function. First, reduce this, because these two are coming parallel. You can simply add these two. That is the reduction of these two, which will become 15. Which will become 15. And you can reduce this. You can reduce this. So what is this reduction? Because this is a negative feedback with unity feedback. You can write that as, so what is that? This is nothing but 10 divided by s into s plus 2 s plus 1 plus 10. Correct? So this is what is the reduction of this. So since these two are in series, you can simply put them in series and then find and write this. Correct? This is minus. So then what is this into this? So because these two are in series, you can simply make a product of that. Can you see this reduces to something like 150 divided by s into s plus 2 s plus 1 plus 10, and when we reduce this, we can certainly reduce this one. Okay, fine, let it be as it is. So now once you're done with this, so can I write this as a single block, and then can I just write this as the ultimate thing? So this is minus, so this is RFS CFS. Then what is the feedback of this one? What I said was you retain this as it is plus the denominator into HFS. So I'll retain this as it is. So it is 150 divided by s into h plus 2 s plus 1 plus 10. So this is the term as it is. Plus what need to be added? Plus 150 into 1. So this is 150. Can you see this is your CFS RFS? We can actually find the roots of it. So what will be this? So if we can simplify this, it is s cube plus s cube plus this is 3s square plus 3s square plus 2s plus this plus this is 160 by, okay, this is 150 by 150. This is CFS benefits. Correct? So if you find the roots of it, now this is of course if you are asked to find the closed loop transfer function of this itself is the closed loop transfer function. Suppose you are asked to find the location of poles and put them in S-plane representation, so you need to go one step further. So what is CFS by RFS? CFS by RFS is, just see what we have done. We have reduced this to 15. We have reduced this to 10 by s into s plus 2 s plus 1 plus of 10. Then we multiply this with this, which is 150 divided by, of course, you have this feedback path is 1. Then how did I reduce the overall block? Overall block is 150. This as it is plus 150. Why this plus 150? Because you have a negative feedback. So now this is the overall transfer function, is it not? s cube plus 3s square plus 2s plus 160. So what is this? So this would be, let me find the, I hope it is, okay, I have this only. Okay, now it is 1, 3, 2, 160. I have roots which is 150 divided by s plus 6.49 is s plus 1.745, and it is plus or minus j 4.64. So I have the poles. There is a pole at minus 6.49. There is a pole at, there are complex poles at real value minus 1.745, and imaginary is, this is the imaginary which is plus j 4.64, this is minus j 4.64. So these are three poles, closed loop poles. And suppose if you want to do using signal flow, because this is how you can so easily find this one, because you know the reduction of this feedback path, you know the reduction of this parallel path. Parallel path into the addition, it is actually 5 plus 10, 15. And what is this? This is of GFS by 1 plus GFS into HFS. That's what we did. Then we multiplied these two because they stay in series. And once you have this one, again, what the Fourier transformation of this? Fourier transformation of this is this. Then you end up with this. Finally, the pole position. Suppose if you are if you want to find the transfer function using what signal flow graph, you can certainly do that. So what we'll do, we'll just identify the takeoff and summing point and try to verify what the transfer function you will get it. So this is one summing point S1, this is another summing point S2, this is other summing point S3, and this is takeoff point T1, takeoff point T2. So shall I write this as my RFS? This is S1, and you have this. You can say this is some T1 dash. You have a T1 dash, and then you have S2 here, and you have S3 here, and you have T1 here, and you have T2 here, and you have CS here. So between this and this, you don't have anything. It is simply 1. Between this and this, it is again 1 here. T1 dash to S2, you have it as 5. You have this as 10. And between S2 S3, it is simply a gain of 1. Between S3 and T1, you have this 10 by S into S plus 2, S plus 1, and you can see you have this between this and this, it is minus 1, and here it is 1, here also it is 1. So now you can use Mason's gain formula to find the, so this is Mason's gain formula, which is nothing but CFS by RFS, so which is nothing but 1 over delta summation of I is equal to 1 to n, or this is okay, k is equal to 1 to 1 pk delta k. So what is k now? K, of course, what is the value of n? N is nothing but number of ways of reaching the output. N is actually 2, then this will become 1 over delta p1 delta 1 plus p2 delta 2. So what is p1? P1 is nothing but how many ways you can go to this. What is p1? It is 1 into 1 into 5 into 1 into 10 by x into x plus 2 x plus 1. Can you see this is into 1 into 1? This is your p1. What is p2? P2 is again this is 1 into 1 into 10 into again 1 into again this is a path. In this path you have 10 by x into x plus 2 s plus 1, correct? you have into 1 into 1. Then you have only this part. So what is L1? L1 is minus of 10 by s into s plus 2 s plus 1. So this is what is only loop available. So then what is delta? Delta is nothing but 1 minus of loop. You have only one loop. And since also on the one loop, there are no non-touching all those stuff. It will become 1 plus 10 by s into s plus 2 s plus 1. Correct. So what is delta 1? Delta is actually 1 minus because all the loops which are there in there is a loop, only one loop here. This will certainly touch this forward path. This will touch this forward path also. So both delta 1 and delta 2 are 1 only. So it is 1, is also 1. So what is CFS by RFS? CFS by RFS is P1. So what is P1? So P1 was actually 50 divided by s into plus 2 s plus 1 into 1 plus of 10 by s into s plus 2 s plus 1. Correct. uh, this is the value, fine. Then what else we have? So this is P1 delta 1 P2 delta 1 by 1 plus 1 plus this value. What is that value? So this value is now, so now can I write it as 1 plus, so what is delta? So delta is actually this, it is 1 by 10 into s into s plus 2 s plus 1. So then you can see in the numerator, you have it as, you have now this is this plus this will actually become, because you can see the denominator is same, so the denominator same results in uh, this plus this is actually, now it is s into s plus 2 s plus 1 divided by, of course this will become, so this is 5 into 10, so this is 100. Okay, this is actually 10 into 10 is, so this is now 150 by so and so. And how about, and we have forgot one more loop. So what is the one more loop? One more loop is this between P2 to S1. So shall we write this also? Where is that? Let me write this T2 to S1. This is minus 1. So I have my second loop. What is L2? L2 is nothing but entire multiplication. So L2 is nothing but can I write it as 150 divided by because this entire thing is 150 by s into s plus 1 s plus 2. So that's what is second loop. Of course it is minus. So let me write this. This is 150 by s into s plus 1 s plus 2. Correct. So this is the numerator. In the denominator I have 1 plus 10 by s into s plus 2 s plus 1 plus of 150 by s into s plus 1 s plus 2. Can you see I have all these components? So now if you can see the denominator of this and these two, here also it's the same term denominator. I can still write it as 150 by s into s plus 2 s plus 1 divided by 1 plus 160 by s into s plus 2 s plus 1. If I take the LCM, then it is 150. This will go with this, but this will be coming here. Is it not s into s plus 2 s plus 1 plus 160? You can see now this is CFS by RFS, which is 150 by s into, of course this will be s cube plus s cube plus 3s square plus 2s plus 160. So this is CFS by RFS by doing it using signal flow graph. So let us just compare that with what we found using the block diagram technique. Block diagram matlab easier way. When I say easier way, it is here. So what is this you have? Can you see this? This is a transfer function what we got using this, okay, Mason's gain formula. Was it not the transfer function got it using the block diagram? Can you see 150 150? Can you see s cube 3s square 3s square 2s 2s 160 160? Now again, what method to use when, it depends on how complex the block diagram is. In this particular block diagram, this is very easy to get a transfer function directly by solving this and then simplifying this. You can do the same thing or same solution using signal flow graph, but it's a laborious process. Because you need to go through all these things and you'll end up with the same transfer function. So now in this particular example, it is easy to get a transfer function without writing a signal flow graph. But in some cases, let us find in next problem why it is so easy to use signal flow graph to find a transfer function of a system. So now let me just show you that. So in this particular case, solving it using the block diagram itself is very easy compared to the signal flow graph. You can see signal flow graph, you need to do all these things. Let me show you one more example where signal flow graph method is easier compared to block diagram reduction. Block diagram way of solving the transfer function of the system. So this is 10. Let me take this as 11. 10 is already over. This is 10. This is 11. This is 12. We can write this as 14. Now let me just try to do this. So let me try to do the feedback for this from here to here. This is V1, V2, V3, and this is assuming that this is some H2 minus, and assume that this is some H2. So this is RFS, this is CFS. Okay. Now, suppose if you start solving it using the block diagram technique, so we know that in block diagram technique, if it is parallel, you can simply add. If it is feedback, you can simply take it as a GFS by 1 plus GFS into HFS. Let us see, is it easy to write the feedback as it is. Just see here, this is one feedback. But in this feedback, you have this also. So you have to eliminate this in this feedback. So elimination of this from this position is a complex quantity. So that you should know certain rules of the block reduction. Again, can I reduce this? You cannot reduce this because there is a takeoff point here. Can I reduce this? Can I reduce this? No, you cannot reduce this because there is a takeoff point here. There is a summing point here. It becomes so difficult for you to find the transfer function of this using what? Block diagram reduction, because you have a hurdle here, you have a hurdle here, you have a hurdle here, you have a hurdle here to reduce this feedback, this feedback, this feedback. See, for reducing this feedback, this is a hurdle. This is a hurdle. To reduce this feedback, this is a hurdle. To reduce this feedback, this is a hurdle, this is a hurdle. So you have so many hurdles. Can I use signal flow graph to find the transfer function? Yes, it's one of the easiest way now. So now identify the takeoff and summing points. So this is summing point 1, summing point 2, takeoff point 1, summing point 3, takeoff point 2, takeoff point 3, CFS and RFS. So you can start here like this. This is RFS. One is summing point S1, summing point S2, takeoff point T1. There is a summing point S3. There is a takeoff point T2. There is a takeoff point T3, and there is a CFS. Now join them. How to join? Between RFS and S1 you have 1. Between S1 and S2 you have G1. This is G1. Between okay, let us take this. Okay, between S2 and T1 you don't have anything. Take it as 1. Between T1 and S3 you have G2. Between S3 and T2 you have 1. Between T2 and T3 you have G3. Between T3 and CFS you have 1. And between takeoff 1 and S1 you have what? Minus 1. Between S2 and T2, between S2 and T2 you have, what you have? You have minus H2. And between S3 and T3, between S3 and T3 you have, this is T3. What you have is minus H3, minus H2. So this is so easy. Now do you have a loop L1, this loop? Do you have this loop L2? Do you have this loop L3? So can I write what is L1, L2? Because by this time you already know what is a loop. Loop is one which has a closed path. So this is nothing but minus G1 L2. Minus G1 is this G1 into 1 into minus 1. So that is L1. L2 is G2 into 1 into actually minus H2. This is minus. So shall I write it as minus G2H2? This is G2H2, and L3 is G3 into minus H2. Is it not minus G3H3? It is so simple. So we have only one forward path here. So that's what is CFS by RFS is only one forward path is there. So it is G1 1 into G1 into this. Can you say it is G1 G2 G3? This is what is G1 G2 G3. The first only P1. What is delta 1? Delta 1 is actually 1. Why delta 1 is 1 minus 0? Because you have 3 loops. All the loops will touch the forward path. So that's why it is 0. So it is into 1. So this is what is P1 into delta 1. And in the denominator you have delta. What is delta? Delta is nothing but 1 minus L1 plus L2 plus L3. Individual loop gains plus of non-touching. L1, L3 are non-touching. L1, L3 are non-touching. So what is this then? This becomes 1 plus G1 plus G2 H2 plus G3 H3 plus what? It is L1 L3. So L1 is G1, L3 is G3 H2. So this is my transformation. You know, it has become so easy to solve the transfer function of such a block diagram using signal flow graph, because it involves just identification of takeoff and summing points, properly identifying the loops. See, L1 L2 touches, L2 L3 touches, whereas L1 L3 doesn't touch. What do you mean by touching? They don't possess a common node. So you can see, using SFG, this is the easiest way of writing the transformation. Suppose if you have used the signal flow graph, sorry, block diagram reduction, so it would have taken more than half an hour or more than that to move this before this and move this before this and move this after this, something like that you would have done. So that is, maybe in the previous problem you might have seen that using block diagram is easier compared to SFG. But of course, it depends on the problem what you are looking into. So look at the problem, decide which method you want to do it. Suppose if there are loops without any takeoff and summing points, you can simply reduce. If there are some hurdles, don't go for what signal flow. Sorry, don't go for the block diagram reduction type of technique. So this will be the easiest one. This will be the easiest one. Of course, depending on the problem, of course, in most of the cases, except the easiest which can be solved using, of course, I will not say that is difficult, but it is roundabout. So the first problem what we saw was, we'll get the same answer, but thing is that we have to go around. But in the second problem, it is so easy to find using signal flow graph. Okay, be able to decide upon which method to use when, and even if you use signal flow graph for all the methods, be very clear with the forward pass, feedback pass, and non-touching things, so you can easily comfortably do it. So fine, so we shall move on to uh, writing the transfer function of a given circuit and then finding its poles and zeros. So let us consider a circuit something like this. So assume that I have a circuit something like this here. So let me just take, so there is an amplifier with a gain 10 here, and let us assume that I have a capacitor and an inductor coming here. I want to know what is V0. So this is R1, L1, C1, this is C2, L2. So let us take this as 1 millihenry. Let us take it as 1 kilo ohm. Let us take it as 1 microfarad. Let us take it as 2 microfarad, and let us take it as 0.5 millihenry. So let me locate the poles and zeros of this system. So now I have to find the transfer function of this. So how do I find the? So this is like, okay, V in. So I have to identify the poles and zeros. So this is what. Let me say it as V1. Let me say this as V2. This is V0. So now I have to get. So there are actually three blocks. One here, one here, one here. So I can just simplify this into, so three blocks. These are the three blocks what I have. So this is V in, V1, and this is V2, this is V0. So I need to find transfer function 1, this is transfer function 2, this is transfer function 3. So what is transfer function 1? So this is actually V2 of S by V1 of S, which is straight away given as 10. This is given as 10. Here I want to know what is V1 of S by V in of S. I need to find, here I need to find what is V0 of S by V2 of S. So I need to find this. So if I multiply this and this, I'll get the overall transfer function, which is V naught of S by V in of S. So I'll get the overall transfer function if I multiply all the three. So let me find what the transfer function of this. Again, there is no need to write the signal flow graph or all these things, because it's easy to find the transfer function easily for this one. So what do you have? You have it as R, you have it as SL1, and you have it as 1 over SC1. So I have this as V1, this is Vn. Okay, Vn of S, this is V1 of S. So what is V1 of S is equal to, or because the voltage drop across this is nothing but V1 of S. So I can write V1 of S by Vn of S as equal to 1 over C1. This is the impedance of this divided by the overall impedance. Overall impedance is R plus SL1 plus 1 over SC1. So now if I take the LCM and all those stuff, it is but this will go with this, so then it will be 1 over is it not so shall I write it as uh, SRC1 plus A square L1 C1 plus 1. That's what is the transfer function of this. Here it is 1 over this. So now you have V1 of S by Vn of S is given by 1 over A square L1 C1 plus SRC1 plus 1. Right? This is the transfer function of this, and this we already know as 10. So what is the transfer function of your V naught of S? So it is V naught of S by V of S, which is nothing but this. So I have this circuit now. This is SL2. This is 1 over SC2. You have V of S. This is V naught of S. So I want to know what is V naught of S by V of S, which is nothing but impedance of this SL2 divided by the overall impedance, which is nothing but 1 over SC2 plus SL2. So what is this now? So then this becomes A square L2 C2 by 1 plus A square L2 C2. So this is my transformation. So now, so what is transfer function 1? Transfer function 1 is this 1 over A square L1 C1 plus SRC1 plus 1 into 10 into what is this transfer function? It is A square L2 C2 by 1 plus A square L2 C2. I have this. Now what is the overall transfer function? It is 10 into A square L2 C2 by 1 plus A square L2 C2 into A square A square L1 C1 plus RC1 plus 1. So this is sufficient to know the poles and zeros. If you can see here, I have a S square term, so naturally that will end up with a repeating zero at origin. Repeating zero at origin. This is overall transfer function. This is V naught of S by V in of S. So this is TF1, this is TF2, this is transfer function 3. Transfer function, third transfer function. Third transfer function. How about this? So this is certainly ending with, so you have, so this is giving me, this is actually indicating the complex pole set imaged point. So it's like 1 plus A square into, so what is L2C2? So L2 is, sorry, point, sorry, it's 0.5 exponential minus 3 into 2 exponential minus 6. Okay, it is, okay, this much. It is actually LC is 1 nano. This is 1 nano, and what you have is Okay, I can take out this L2 seat outside, can play with that, or it will be the same. Then what you have, so this is a square. What is L1 C1? It is 1 exponential minus 3 into 1 exponential minus 6. It's actually again 1 nano plus s into, what is this? This corresponds to C1. R is 1K. 1 exponential 3 into C1 is 1 milli, 1 micro, 1 exponential minus 6 is 1 milli. It is 1 milli plus 1. So here, this will certainly yield me. This will certainly yield me. Okay, this has got poles at A or to the power of, okay, 10 power 9. Okay, 1 exponential 9, okay, under root of 1 exponential 9 is actually 30 plus or minus k, 31.622k. This is minus j, 31.62. This is the poles imaginary axis. And how about these poles? So here the poles are, let me just find the poles. 2, it is 1 exponential minus 9, next it is 1 exponential minus 3, next it is 1. The poles are at, uh, minus 1001, and other is at, okay, other is at minus 998.998. So this is resulting in repeating zero set origin, uh, imaginary poles on the imaginary axis at plus or minus j, 31.62k, and a pole at minus 1001, and a pole at minus 998.998 kilo. So these are the four positions of this particular circuit. You have something like this. This is this, and you have this here, this here. If you want to simply write the transfer function, the transfer function is only this. The transfer function is only this. If you want to exactly locate the poles, substitute the values of each inductor and capacitor, you will get the pole position. And let us try to move to a simpler problem, if so-called simpler problem. Suppose you want to find out the transfer function of this. This is R1, C1, L1, C2, R2, C3, R3. This is V0. This is V. So you have to find what is V0 of S by V of S. If you want to know this. So replace each term by its Laplace. It is 1 over SC1. It is SL1. This is 1 over SC2. This is 1 over SC3. So identify the loop currents I1, I2, I3. Identify the nodal voltages V1, V2. This is V0. So write the expression for each one of them. What is I1? I1 is nothing but V in minus of V1 by R1. V1 is nothing but it is I1 of S minus I2 of S divide by the impedance. Divide by impedance, which is nothing but SC1, because 1 over 1 will become so and so. What is I2? I2 is nothing but V1 of S minus V2 of S by SL1. What is V2 of S? V2 of S is nothing but I2 of S minus I3 of S divided by 1 over SC1, which will become SC2 multiplication. What is I3? I3 is nothing but V2 minus V0 divided by impedance. So impedance is R2 plus 1 over SC3. So to simplify this, this comes like as SC3 V2 minus V0 by 1 plus SR2 C3. This is your I3. And how about V0? V0 is I3 multiplied by R3. So you know this, 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 you know this. So now start writing the ZG. So start with Vn, go to I1, next it is V1, next it is I2, V2, V3, V3, V3 or V0. So plug in this. So what is I1 is? So I1 is Vin by R1 and this minus 1 over R1. What is V1? It is I1 into SC1 and it is minus of SC1. So what is I2? I2 is V1 into 1 over SL1 and it is minus 1 over S. And then what is V2? V2 is I2 into SC2 but it is minus of I3 into C2. What is I3? I3 is actually V2 into SC3 by 1 plus SR2 C3. And how about this? This is minus of the thing. So here it is minus of SC3 divided by 1 plus SR2 C3. Then what is this? This is actually R. There is only one forward path. This into this into this into this into this into this will become P1. Delta 1 is 0. Identify loops 1, 2, 3, 4, 5 loops. So if I want to write, okay, I'll just leave it to you. How do you get the transfer function? So you have loop 1, loop 2, loop 3, loop 4, loop 5. So here it is P1 delta 1 by 1 minus of L1 plus L2 plus L3 plus L4 plus L5 plus of non-touching loops L1 L3 L1 L4 L1 L5 plus L2 L4 plus L2 L5 plus L3 L5 minus of 3 non-touching L1 L3 L5. So this is, you have to know what is L1 L2 L3 L4. So this is your V naught of S by V. Of course, usually in the examination, you may not be asked to find the pole position of such a complicated circuit, but you may be asked to find the pole position of a simpler circuit as it was discussed in the previous case. This is also a bit involved, but again, it's easy to find the pole position. You can see where are the poles. This is now in what pole zero form. You can simply write, okay, this is one pole, a set of poles here, complex which are imaginary, and you have a set of, so it's like, okay, This is, so you're trying to identify the pole position. Here also you can solve for this. You can get the transfer. Okay. So in this video, we will stop now here. So this is how you can able to find the transfer function of any given circuit diagram uh, by writing the signal flow graph and then solving it for the signal flow graph. Thank you.